So today I'll talk about two topics, which are fundamental astrophysical processes. The first is magnetospheric accretion. The second is companion disk interaction. And I want to make my discussion as general as possible, not limiting to protoplanetary disks. But first I want to thank my group members. So I particularly want to thank CCA for hosting Stanley Burnett, who was here last semester for the pre-doctoral fellowship. And I clearly see Stanley's tremendous growth after coming back to UNLV. So thanks for that. And Yihan Wang, I did some AGNDs. I'll show some work with Yihan. And I also want to mention this work. That is Yihan did Rosaba here. So for companion star, interact with the system with two planets and eject both planets. And we propose this could be a way to produce Jupiter mass binary objects. So I encourage you to talk to Rosaba on this very nice work. And I have two grad students who graduated, actually defended last week. And Ian Robago will go to Milan and work with Giuseppe, who is visiting CCA here. And Sanja, who will go to Colombia to start his Hubble Fellow, and then he will come to CCA for 1 year. So it seems they are all in good hands. So good. So today I'll talk about something I have been working very recently on magnetospheric accretion with the help of my new student, Arturo. So to start with, we know that accretion systems are at all scales. So we have a supermassive black hole that's at the megaparsec scale. You see this beautiful disks, and you have jets along the pole direction. And then the smaller scale, you have SS433. This is a stellar mass black hole. And you have this wobbling jet. And this jet is actually caused by a misaligned disks around black hole, and because it's misaligned, the disk will precess. So this precession causes this wobbling jet. And even smaller scale, you have protoplanetary disks. This is the Accretion system, perfect adjunct systems, and you see this beautiful jet. And when you add a smaller scale, the time scale are also faster, shorter. So you could take a time evolution. You could study the time evolution of the features. And the jet here produced at around 200 kilometers per second. So you can see here at dramatically different scale, from megaparsec to parsec, we have the same physics, accretion disks and the jet. So another universal process is companions inside the disks. So at very large scale, we have satellite galaxies like M51 satellite galaxy inside these beautiful spirals, grand design spirals. And this is actually probably the first image of M51, and actually it's from a sketch. It's a drawing, and at that time they probably still don't have the photograph. So we have these grand design spiral and the companion together. And at the protoplanetary disk scale, you see these grand design spiral arms, and they could be related with a companion in the disk too. So if you look at these images, they are remarkably similar. And at even smaller scale, you could have 8-kilometer wide moon inside a huge wave in Saturn's ring, and this wave is 1.5 kilometers high. Although in Saturn's ring, the ring is only 10 meters thick. So this is a huge wave and casts a shadow to the ring. So the companions put in disks at very different scales. So these are the two topics I'll talk about. The first is on accretion process. The second is on a companion and disk interaction process happening at different scales. And then finally, I'll try to put them together to discuss specific application about how Jupiters interact with the inner part of protoplanetary disks. So we start with magnetospheric accretion. Magnetospheric accretion is a very general process. You only need a magnetized star, and you only need the accretion disk. And the accretion disk will try to accrete onto the magnetized star. But at some point, the magnetic pressure from the stellar magnetic field is so strong, then the material has to climb the magnetic field and accrete to the star. Okay, so this is magnetospheric accretion. It was first actually proposed or studied in the low mass X-ray binaries. So in these systems, you could measure the spin of the neutron star, and the magnetospheric accretion is important for the spin evolution, and it was also thought to be related with the quasi-periodic oscillations in neutron star system and low mass X-ray binary. And recently, people suggest that it's even related to these ultraluminous X-ray sources. For young stars, the magnetospheric accretion produces the accretion signatures. And there also leads to disk variability, and is important for planet formation. And we also think magnetospheric accretion could even happen around the young planets. For example, Jupiter may once have gone magnetospheric accretion. And for equiterrestrial systems, we have this beautiful ring in PDA-70 system. Is a classical T-Tauri star. And there are two planets, young planets, within the gap of PDA-70. And these two planets actually emit H-alpha lines. And the H-alpha line emission could be due to the magnetospheric accretion onto the planet. So this is magnetospheric accretion. So first, I will start some observation from neutron stars, low mass X-ray binaries. So the low mass X-ray binaries provides us a very precise measurement on the central neutron star rotation. So there is a big mystery on the spin evolution of neutron star. So for example, in this system, the neutron star spins up, and suddenly it has the spin reversal. So it's like spinning down, and then it spins up again. So this sudden change seems does not correspond to any change in the X-ray flux. But the recent measurement could kind of have very precise measurement on the recent this torque reversal event. And they could measure the slope of this spinning down and spinning up. And this is a spin up or spin down and spin up rate. And this rate somehow correlate with X-ray flux very well. So this suggests that the neutron star spin evolution is tightly related with your disk size. So that's some evidence on a magnetospheric accretion happening around these neutron stars. So for young stars, the young stars have kilogauss magnetic field, not as strong as a neutron star, but it's strong enough to truncate this protoplanetary disk. And material, when they move to around several stellar radii, then they will start to climb the magnetic field and accrete it onto the young star. So if we zoom in this point where there's a free falling material onto the stellar surface, you could calculate the structure here. They will form a shock because it's a free fall speed, very high speed. They have a shock at the stellar surface. It will produce a temperature around 1 million Kelvin. So it will provide like a lot of X-ray fluxes. But these X-rays will be reprocessed by the stellar surface in a very short distance. And the causes hot spot on the surface around 7,000 Kelvin. So this hot spot will provide a UV access on top of your stellar photosphere. Okay. So in protoplanetary disk observations, we clearly see these heated photosphere. So this is from the hot spot. And you just integrate all the flux in the hot spot, and you could actually use this energy argument and derive the disk accretion rate. So this is how we measure protoplanetary disk accretion rate, just by using this excess UV flux from the hot spot. So this hot spot not only important for the disk accretion rate estimate, but also important for the outer disk too, because UV photons are very efficient to drive photoreaction and drive disk chemistry. So chemistry is mostly driven by these high energy photons like UV. So this magnetospheric accretion could also affect the chemistry further away from the star, which is important for JWST and AMA. So magnetospheric accretion will also affect exoplanet formation, because if you look at all the system and put the scale here, the magnetotruncation radii is around 0.05 AU. And the whole inner disks within 0.1 to 0.5 AU are threaded by this strong stellar magnetic field. They will be very turbulent. And if you look at the protoplanetary disk statistics, this is where 0.05 AU is, this is where 0.5 AU. The majority of discovered exoplanets are in this inner region, which are affected by the magnetospheric accretion. Okay. So due to the importance of magnetospheric accretion, Hubble Space Telescopes have carried out so far the largest director's decretionary program, the DDP program. So the previous DDP program including an upper deep field or ultra deep field, and this is even bigger than those ones combined. Yeah, Hubble spent 1,000 orbits observing both low mass stars and high mass stars, and 500 orbits were observing for these low mass stars. They observed around 70 stars around different ages and around different stellar masses. And what they get is this hybrid, the spectrum from UV to optical. So while this program was carried out, actually 3 weeks ago, there was a conference at Space Science Institute, which marked the end of this observation run. The final data released, all the data have been released several weeks ago. And at the same time, over the past 4 years, when Hubble was doing these observations, on the ground, there are big collaborations in the US and in Europe. They use all the telescopes from X-ray to optical near-infrared, some doing photometry, some doing spectroscopy to monitor these 70 stars simultaneously. So it's a large community effort with more than 100 astronomers participating in all the observations. So this was the first paper from this collaboration. So we can see that people monitor these systems over many days at different bands. And then during these times is where Hubble observed this system. And Hubble actually only observed the UV part. And in Europe, people use VOT, got the extruder data from the optical all the way to infrared. So from this high precision photometry or spectrum, people could study how the hot spot on the star look like. So they could actually distinguish that the different hotspots, some hotspot has much higher temperature and some hotspot at a lower temperature. They can also study the hotspot distribution on the surface of the star. So, and this shows that how the hotspot changes for one of the systems. So we can see that for the low density region, where the hotspot is a little bit colder, the covering factor does not change much. But for the hotspot, the covering factor could change dramatically within a short time. And the interpretation was that the hotspot rotate out of a line of sight. They rotate to the back of the star, so get blocked by the star. So now combining this high resolution spectroscopy observation and a time-dependent observation, we are able to study the hotspot distribution on the surface of the star. So while observers spend a lot of time to get all these data, the theory behind this magnetospheric accretion is still quite uncertain. So we know this traditional picture where you have accretion disk on the magnetosphere and things climb to the magnetosphere, but the detail is still uncertain. For example, Frank Xu once suggested that the conducting fluid cannot allow magnetic field to penetrate through. So all the magnetic field has to be pinched up at the inner edge of the disk. So this is the famous X-wind model. So this magnetic field produce an X-wind, and which could carry the high temperature processed material to further out in the disks. So this is very popular in the meteorites community. People think this is a mechanism where you could produce CAIs, calcium aluminum enriched material far away into the disks. On the other hand, if you think the star and the disk rotates at different rate, then the magnetic field will be winded up, right, naturally. So whenever the field gets winded up once, then you will have reconnection event and produce these magnetic bubbles and will inflate. So this will lead to kind of episodic outflow. So it's not a steady state. In order to get a steady state, you need a very high resistivity. So all of these still needs to be tested. So simulations have been carried out before. So some pioneering work carried out by Miller and Stone. At that time, they could only do 2D simulation and only for 2 orbits. And then later, people have carried out 2D non-UMHD simulations, which allow the material to pass through the field and accrete it to the star. And then 3D IDMHD simulation have carried out with these very special grid. But also, they can only do a very short time scale because very computationally expensive and kind of focus on the geometry around the within the magnetosphere. So with these things, with the new tools, we want to answer questions like where are the accretion occur, whether it's really from the pole as people expected, or there actually could be accretion at the equator, and whether this accretion is steady or non-steady, and how the outflows are launched in the systems with this complicated field geometry, and how this accretion affects the central object spin evolution. So we carried out Athena plus simulation with the Cartesian grid, but with the 7-level refinement. So we have a star in our computation domain. This star is actually resolved by 1 million grid cells. So we could resolve the stellar structure, maintain a hydrostatic central object. And the star has a dipole field, and the star in this simulation is non-rotating. So it's the simplest configuration you could think of for magnetospheric accretion. Non-rotating star with a dipole field and a accrete from east. And we can run the simulation for 2000 orbits. So this is how the simulation look like. So first you notice that this is very turbulent, it's highly turbulent. And then you notice that this is very thick, magnetic supported disk. And then you have these filaments could penetrate through the magnetic field. There's like fingers moving in. And when they move in, some of them will start to climb the magnetic field. Eventually they climb the magnetic field onto the star. So they form this onion shell-like accretion structure here, onion shell-like structure. So if we make a polaroidal cut of the simulation domain, we can see that although there's a density drop at the midplane, but the density change at higher latitude is less. You have continuously mass distributed from this very thick magnetized disk. So this is different from the traditional picture. And the second thing is that if you look at the midplane, then you have these fingers moving in. So if you think what this happened is actually a really Taylor instability. If you just focus on the vertical direction, you have high density material on top of a low density material. The low density material is magnetic supported. So this is really Taylor unstable, high density on top of low density. So it forms these fingers. And people have seen these in previous viscous simulations. And this is a lab experiment I did 1 month ago. To show the really Taylor instability. You just put the milk in the water because milk is a bit heavier than water, so they sink in, forming these nice filaments. So due to these penetrating filaments, they will eventually get to the star, then that will affect the hotspot distribution of the star. Right. So most of the mass still falls from the pole, around 30 degrees. But you have these penetrating fingers, which could accrete to the star at the equator. And it depends on the stellar size. If the star is bigger, of course, then you will have more fingers reaching to the stellar surface. So you will have a more equator accretion than polar accretion. So overall, we find most accretion through the pole, but we still have these equator accretion. And the hot spot actually cover a very small region in the star, only cover less than 20%, roughly consistent with observations. And we are still doing more detailed analysis compared with these new observations where they have different hotspots, temperatures. We are comparing our simulation with them. Yeah, so this is still something going on. And then we could measure how the material when they impact the star, what's the speed? So the speed is almost free fall speed, consistent with observations. So you could see these shocks. Okay. So we could also measure the accretion rate onto the star. The accretion rate, surprisingly, is quite steady. So the standard deviation for the accretion rate is around 20% onto the star. And the recent Ulysses program have monitored TW Hydra, and people have monitored for 25 years. They found very similar like accretion rate, like variation. Okay. So because the theorists and observers always use different units, so in order to compare them properly, you need to like flip this image like left and right. But after you flip it, you will look at the shape looks similar. Observation has a little bit wider distribution than theory simulations. But our simulation is not particularly geared towards TW Hydra. So there are still things we could compare further in future. On the other hand, we find the outflow is quite unsteady. you have these peaks. And the outflow rate in this case very low, less than 1%. Something new we discovered is that if you look at the mid-plane sometimes produce these very large magnetized bubbles around the magneto-truncation radii. So you see these magneto bubbles produced in the simulation, and they orbit around the star at subcapillary speed, and then they disappear. And later there could be another magneto bubbles produced. So this is the extreme version of this really tailored instability for the interchange instability. It's actually very similar to the magnetosities around supermassive black holes people have done before. So you see these magnetic bubbles here and here. So it's quite interesting to see the same physics happen at very different scales in very different scenarios. But in this case, you all have these magneto bubbles produced around the very highly magnetized objects. And these magnetic bubbles will cause modulation to the accretion rate. So that's a theory prediction that you will, if you look at the periodogram for total mass accretion rate, there could be a peak around several orbital periods at the truncation radii. And if we look at the mass accretion rate at one annulus of the star, basically it traces the hotspot movement, you see the same period. So that's a theory prediction that we should see some quasi-periodic oscillations in protostar observations. And maybe this could explain the QPOs in X-ray binaries. So the next step we did is that we start to consider the stellar spin. In the previous simulation, we did not consider the stellar spin. Now we include the stars. We allow the star to spin. So when the star would spin, then you introduce another free parameter, how fast the stars will spin. So this leads to a co-rotation radius. So co-rotation radius is defined as the part in the disk where the capillary frequency of the disk matches your stellar frequency. So basically at the co-rotation, the magnetic field is frozen with the star. Okay. So for the non-rotators, so in the extreme cases, the co-rotation radii could be at infinity in this way. When the star spins up, the co-rotation radius decreases. But as long as the co-rotation radii is larger than magnetotruncation radii, the accretion process will add angular momentum to the star. So the star will spin up. And it's expected that the equilibrium state will reach when the co-rotation radii equals the truncation radii. And if the co-rotation radii is smaller than the truncation radii, we would say it's in a propeller regime, it will eject, you have a strong outflow. So we carried out 4 different simulations. These 4 simulations have different co-rotation radii. So these 2 are the slow rotators, and these 2 are the fast rotators. So if we look at the simulation, and as expected for slow rotators, similar to our previous case, you have these magnetic bubbles, and then you have these filaments, fingers. But when the spin rate increases, you see that the bubbles become less obvious. In this case, you still have a lot of fingers. But in this case, you almost don't have fingers at all. So clearly the rotation of the star suppresses this interchange or really tailored instability. So the bottom line here is the spin suppresses these instabilities. And then you are expecting a more accretion from the pole instead of through the midplane. And this is what we see from the hotspot distribution on the stellar surface. So for faster rotators, you have hotspot only at the surface. For slow rotators, you could have small spots at the equator. And we also calculate the periodal diagram. And for slow rotators, we do see these modulations on the accretion rate at a frequency around the spin frequency. But on the other hand, we also see a lot of other peaks. These other peaks corresponds to like several times the orbital frequency at the radii. So these QPO signals still persist even with the faster rotator. So yeah, not all hotspots orbit at the spin rate of the star. You have these quasi-periodic signals. And we could also measure the accretion rate. And the accretion rate is always kind of steady unless you are in the propeller regime. And the accretion rate actually decreases. The outflow rate increases. The scale on the left and right panels are different. That's because the outflow is much stronger in this case. But they are all showing these peaks. So while I gave this talk at Space Telescope Science Institute, I was reminded that there was an observation paper last year with exactly the same, almost same title. It's a stable accretion and episodic outflows in German region. So we are still doing more detailed analysis on the time scale of these episodic events. But so far, it looks like the simulation kind of agree with the observations so far. So we could also measure the outflow rate to the accretion rate, calculate the ratio. So as expected, with the faster spin, the outflow rate is stronger. And we also measure the torque on the star. So for slow rotators on the left side, the torque will spin up the star as expected. For fast rotators, it will slow down the star, the accretion. And the equilibrium state reached when the truncation radii equals rotation rate. So we have confirmed this analytical expectation that you will reach equilibrium state with these two matches. So this during the equilibrium state, the outflow rate is around the 13% of the accretion rate. Also roughly consistent with photoperiod observation, the outflow rate is around 13%, 10% of the accretion rate. And this is here we do not have any disk field at all. All these magnetic field come from the central star. So if you wonder how the equilibrium state, spin state look like, this is how the equilibrium state look like. It's a movie. So you can see the accretion from the pole, magnetospheric accretion from the pole. And you also have filaments coming in from the midplane. And sometimes have these smaller loops around the star. So these patterns are artifact. It's just the breeding of the simulation. Yeah. But this shows that the whole environment is very dynamic. You have accretion from the pole, from equator, and they happen at very short time scale. So during the equilibrium equilibrium spin state, you still have filaments moving in, and you have hotspot, and you produce jet naturally in this simulation. The jet there could have 500 kilometers per second jet launched by the magnetospheric accretion. So to summarize this part of the talk, so we have carried out simulation to study magnetospheric accretion for slow rotator to fast rotators. And we clearly see the interchanging instability for slow rotators. And this instability is suppressed for fast rotators. So the accretion will change more from equator, both pole and equator accretion, to more like a polar accretion. And also the outflow gets stronger when the spins faster, and the outflow rate can reach 40%. So there are many theoretical predictions, such as the hotspot distribution, where they are, and outflow rate related with the spin rate. And we still need to test these in future. So there are indeed some programs in future, like this SPEX mission led by Neil Turner. It's still at early stage, but they want to carry out a test similar mission, but doing at UV. And one of the main science is to observe young stars for a period of time to see how the magnetospheric accretion affects, how the magnetospheric accretion could change for different stars with different stellar spin rate. So we will be able to constrain some of the theoretical predictions. Yeah. So for the rest of my talk, I'll talk about the companion disk interaction. So we know that in protoplanetary disks, we have companions in the disks. And the companion mass to the central star mass could be 10 to the -7 for Mercury or 10 to the -3 for Jupiter. But this same kind of scenario, companion disk, could also happen in AGN disks. For example, if you have a star cluster around the supermassive black hole, the star cluster may interact with the AGN disks. And in this case, the companion, they are stars and black holes. So the mass could be 1 to 100 solar mass. So the ratio between companion to central star mass ratio is similar to protoplanetary disks. So they could share the very similar dynamics. And recently, we may have some direct evidence on this stellar disk interaction for the galactic scale. Like these are the X-ray QPEs, quasi-periodic ejections. They could be leads to a star passing through a disk around supermassive black hole. Okay. On the other hand, if you look at how to observe these systems, it's much easier to observe these systems in protoplanet disks. The angular size of the protoplanet disk is 1 arcsecond. You could get high fidelity images, but it's much harder to get AGN disks much further away. So companion interact with the disks basically through the gravitational interaction. We probably have seen this similar movie many times. If you are in the rotating frame of the planet will excite these spiral arms, and if the spiral arm is strong enough, they will produce gaps in the disks, and these gaps are actually unstable to stabilities and produce large-scale asymmetry. So a low mass companion could lead to large disk structures, and we kind of have seen all of these structures in protoplanet disks. So this is with the assumption of a circularly moving coplanar disk. So I have worked on this planet disk interaction since my postdoc at Princeton. So previously we have tried to explain these spirals with companion. We predict there's a companion here, but recently observation, some of them say there's a companion here. This spiral arm, not very predict. But anyway, the companion could excite spiral arms here. And we have also tried to feed some of the gaps observed in AMA. Like here, we were trying to feed all the 5 rings in this system with a single planet. And we can do that with a planet at 100 AU. This single planet will actually produce 5 rings in this system due to some wave interference and match population. And we also put 2 planets in PDA-70 system and try to match AMA things. So we have tried to just use the coplanar planets or low mass companion disks to feed observations. But at the same time, we will clearly see some limitations of this coplanar circular orbit. Because in some of the disks, you see that the protoplanet is actually broken, like here. Like this disk kind of broke, and this disk broke. So this is not a real disk broken into pieces. These are illumination effects. So what really happened is that there is an inner disk that is misaligned with outer disks. And this inner disk casts a shadow at its nodal position. So what you see, the dark part are actually shadows from the inner misinclined disks. Okay, so in both cases, they cast a shadow. So if you think that these misaligned disks are actually caused by some misaligned companion in the disks, that clearly says that we need to study some inclined companion and disk interaction. So at a larger scale, you will not expect the nuclear stellar cluster interact with the disks in the disk plane. Right? The nuclear star cluster have orbits in all sorts of directions. So when they interact with the disk around supermassive black hole, they could be in all directions at different eccentricity also. So this leads to some further considerations on the planet disk interaction. We need to modify some previous theory. So if you only consider circular orbit, although the planet seems to moving very fast in the disk in the Kepler speed, but the disk is also moving at Kepler speed. So if you just look at the relative velocity, it's actually very small. Around the planet, the flow is subsonic. Only at a distance beyond the disk scale height, the flow becomes supersonic. So the planet is actually in a subsonic environment. And this is not true if you have an eccentric planet. If you have an eccentric planet, the planet will undergo the epicyclic motion in the rotating frame. As long as the eccentricity is larger than h/r, okay, this motion will be supersonic. So the planet will feel a very strong like headwind, for example. And the same is true for inclined orbit. As long as the inclination is larger than aspect ratio, the motion is supersonic. And in protoplanet disk, this number is around 0.05. In AGN disk, this would be 10 to the negative 3. So a little bit inclination, or a little bit eccentricity will lead to supersonic motion between the companion and the disks. And we know on Earth that if you have supersonic motion, you will form boson. You will have a shock formation. So then we say, okay, we want to study this in more detail. And if you have objects moving in a gas at supersonic speed, on Earth we know you will feel aerodynamic drag. And this is when the in the case when the gravity is not important. When the gravity is important, we are in this dynamic friction regime, then the gravitational force will interact with the wake gravitationally. So the relationship between the force and the velocity in these two cases are opposite. So for the aerodynamic drag, the force is proportional to velocity squared. Similar to our common sense, if we run faster, we feel like more headwind. But in the dynamic friction, this is inverse proportional to squared. So if you move faster, dynamic friction is actually weaker. So so I think these are interesting problems. So I give them to students in my computational physics class. I'm teaching a computational physics class. There are students wants to do like they need to do a semester project. So I say, okay, this is easy setup. You guys could try it. So one group tried this dynamic friction problem. Simply put a gravitational source in the simulation domain, and they measure the gravitational interaction between the wake and the source. And then they verify that indeed the force gets weaker at the same expected squared inverse law. Then now I say, okay, this has been seems to be set up. How about this? And this is much harder to do, right? Because this is an engineering problem. You have a solid surface in a flow. So that's what people study airplanes, how they fly, the rocket. It's not what we normally studied in fluid code. And I don't think any astronomical fluid code has solid body inside it. But during the Athena conference 1 year ago here at CCA, we heard talks from engineering people who use the Athena for engineering project, and they could put any sort of shape in their simulation domain. I was very amazed. So I contacted one of the engineering people gave the talk, Nurem Kozak, and he pointed out me to these literatures in their field. And after reading them, I said, oh, that can be implemented. So this semester, I have a student in the same class, computer class. I think he's good enough to implement it. So I persuaded him to implement it into Athena++. So he successfully did that. So now we have a solid body in the flow. And then it formed a shock, very strong shock. And we could verify the aerodynamic drag. So I think this is a very useful setup because you could replace this central object as planetesimals. So you could study how planetesimals move around the stellar atmosphere. And if the central source is a star, you could simulate this is a planet, you could study how the planet gets engulfed by the star. Or if the central object is a star, you could study how the star spirals in the common envelope phase. Or it could be how the stars move in the black hole, in the supermassive black hole disks. So there are a lot of applications for if you allow a solid body in the computing domain. Or it could study X-ray QPEs. Yeah, so anyway, so we have carried out these study these drag forces. But at a larger scale, we could also work out how the spiral will change. So as we know, if the companion has zero eccentricity, the spiral is quite steady. It's like it's built for spirals. But if you have eccentric companion in the disks, the companion will excite is bow shock, and these shocks will propagate in the disks. So you will have very dynamic picture. The spiral is not steady anymore. It will move around dynamically. But you could still figure out the theory to explain these spirals. This is like when you have a boat moving in the water, you could still figure out where the wake is by just adding a lot of these circles. So this is what we did for these eccentric planets. We could have an analytical theory to reproduce these spirals in a time-dependent sense. So as long as the companion is not in purely circular coplanar orbit, the spirals will change all the time. And there were some observational evidence that for some of the systems, you see these two spirals seem to move at different rate, change very slightly, but at different rate, and that may be indication that the different spirals may move at different rate. So in future, we may be able to use these spirals to do something like this seismology. So another application we did was with the EHAN, is studying the nuclear cluster interact with the AGN disks. So nuclear cluster, you could have both stars and the black holes. They will interact with the disks in highly inclined orbits. So he So if we just take one inclined orbit as one example, it's mildly inclined, and we zoom in this part. Okay. So as we know, the companion will passing through the disk, right, at Kepler speed. On the other hand, the disk is also rotating at Kepler speed. So the relative motion between the companion and the disk is actually almost perpendicular to the disk direction. So this will give you a dynamic friction or aerodynamic drag almost perpendicular to the disk. So the force will be in this direction. So then if you calculate the torque, Rf, then the torque will be tilt the orbit of the interacting companion, the orbit. It will try to align the orbit to the disk plane. So all this interaction will lead to like everything become coplanar and embedded in the disks. So Yihan worked out carry out unbody simulations and also carry out the analytical theory and figure out there's a constant integral of motion. But one important thing is that even if your orbit, the companion orbit starts as retrograde orbit, so if the disk rotates this way, companion rotating opposite way, they are slightly misaligned. This companion will flip its orbit. Okay. It will flip orbit 180 degrees, eventually align with the disk. Okay. So this is due to this dynamic friction. So during this flip, if you want to conserve this integral of motion, your orbits will shrink dramatically. Okay. If imagine is 180 degrees, this term is basically zero. So if you're perfect 180 degree orbit, when they flip, they will actually end up in the black hole. So that suggests that for some very retrograde orbit, when they flip, they can be tidally destroyed, get into the tidal destruction regions. So if you have this mildly, but still significantly inclined, so they will be eventually destroyed. So for a more less inclined orbit, they will end up in the disks, and you will, given not enough time, all of the nuclear star cluster, the stars and black hole will end up in the disk. So you could have very packed system. So the stars and black holes are so packed in the AGN disks, it's possible to directly form binary black holes or binary stars. And these captured TDEs, they are very different from the traditional TDE because they are not in parabolic orbit. They are in circular orbit and the slow TDE. So maybe we say, okay, maybe relate to AGN. We're not quite sure. So I have talked about this companion disk interaction. The last 5 minutes, I'll try to put them together and study how, if you have a planet or companion at the inner part of the magnetosphere, how they will interact with each other. They applies to all of these closing planets. So the first thing you notice that these planets probably will feel the stochastic force because the disk is highly turbulent. But if we get rid of this stochastic force, we could still estimate what's the migration time scale. And it turns out the migration time scale is quite long. And we figure out that is because in our simulations, the disk is very turbulent and alpha is very large. If we measure the alpha parameter in our simulation, alpha is close to 1. But people previously assume alpha is 10 to the negative 3 in this region. So in previous calculation, the surface density at the inner disk is 1,000 times higher than what our simulation suggests. So with this low surface density, the time scale for the particular type 1 and 2 migration time scale could be actually longer than the Hubble time scale, longer than the disk gaseous disk time scale. This is 10 to 6, and this is 10 to 7 years. So we don't think the planet could migrate significantly in this region. And then when the planet gets to the inner part, then we find that there is no resonance because the inner part of the magnetosphere co-rotate with the star. They rotate at very different frequency than the planet. So unlike planet, you have mid-motion resonance. Here, the material is rotating with the star. The planet is at totally different orbital frequency. So there is no type 1, type 2 migration in this region. Instead, the planet will feel very strong headwind. So they will feel the aerodynamic drag, like what we showed before. So if you consider the aerodynamic drag in this part, the time scale again is very, very long. So this probably is the only region in protoplanet disk where the aerodynamic drag for planet becomes important. We talk about, we know the aerodynamic drag is important for dust particles, and this is where the aerodynamic drag for planets. So overall, we think the migration in this whole inner region could be very inefficient. So in order to produce these planets which are observed by the Kepler systems, they either need to get there very early when the disk is very massive, or they need to get there through like unbody interactions at a later stage. And if you ask where most of the planets should be to be in the disks, we favor that they could be at the inner edge of the dead zone where the surface area is very high. So we want to test these with numerical simulations, and this is what we did. So my student put a planet in the simulation. It's a hot Jupiter. It's a 10 Jupiter mass planet, and you can see the Jupiter's like CPD. So I'll play a movie for that simulation. So I challenge you because there are 3 planets in this movie. So I'll see if you can see all the 3 planets in this movie. So there are 3 planets, remember that. So this is magnetospheric accretion, and then you have 3 planets in this movie at different distance from the star. You can spot all the 3 planets. Right? So now we spot all of them. Yeah. So the first planet you notice is this one, and this one is actually not a planet. This is circumplanetary disks. When we first see this, I thought, why the circumplanetary disk is in the vertical direction? But then we figure out that because this planet has magnetospherical truncation radii. So the flow at the magnetic truncation radii is actually in the vertical direction because materials start to climb the magnetic field at the previous star. So when the background flow in the vertical direction, sometimes you could produce the CPD in the vertical direction. But that's not always the case because it's very dynamic in this region. Sometimes the disk will still be coplanar. But in this particular case, this planet have a vertical circumplanetary. And you also notice the planet further away. This is the planet, the outer part, outside the magnetic truncation region. And this disk has like a coplanar, the traditional coplanar disk. And you may notice there is a third planet is within the magnetic truncation radius, which is this one. And because the fast relative motion between the planet and the magnetosphere, because the magnetosphere is not rotating here. So this planet is tidally stripped away. And because the relative velocity is so high, the boundary accretion radii is smaller than the planet smoothing the small simulation. So this planet won't be able to accrete. Instead, it will be this, probably it will be between these 2 away. So this suggests that accretion within the magnetosphere is very difficult for planets. Planets will not be able to grow when they get into the magnetosphere with very strong headwind. And these could have all sorts of orientations. And finally, the final slide, that we also observed that some of the planets gather circumplanetary disks, and their circumplanetary disk actually brings stellar magnetic field to the planet. So it's like the planet steals magnetic field from the star. Our planet is not magnetized, but the CPD is magnetized. Because the material from the star is magnetized, when they get to the planet, they bring the stellar magnetic field to the planet and co-moving with the planet. So now the planet the planetary system has a magnetic field. Although initially they don't have, but now they have magnetic field from the circumplanetary disk. And these circumplanetary disks have formed a magnetosphere around the planet and form a bow shot. So this is very similar to our Earth, has a magnetic field and moving in the solar wind has a bow shot. And in here, we also have a bow shot, and this bow shot is actually produced by the magnetic field from the circumplanetary disk. So you can imagine if you have a black hole in agent disks, although the black hole does not have magnetic field, but the disks around the black hole, the black hole disks may have magnetic field. So they may also form a bow shot in the whole system. So the whole system has magnetic field. So yeah, that's all I want to talk about. There will be a lot of observations coming out from both Spitzer observation and community. And it's a great time to carry out these first principle MHD simulations to compare with observations, particularly on the hotspot distribution. and also outflows and other things. And studying companion disk interaction seems very important now for both inclined and eccentric companion, not limit ourselves to circular orbit. And they have application for protoplanet disk and AGN disks. And we are studying the interactions of hot Jupiters and the inner part of the protoplanet disks. Our ultimate goal is to carry out these first principle simulations and understand the environment around the young star and understand how planet could form and grow in this environment. Yeah, that's all. Thanks.
Questions? Are you first?
Excellent talk. I have lots of questions. I'll stick to one. What happens as you increase the mass of the star so that it's pumping out more radiation and presumably you have this magnetospheric accretion? Like, would you expect more massive stars to have lower spins on average because of that? Or is there something else going on?
So overall, you expect that, leads to this one. Overall, you expect that if the magnetosphere is smaller, the star will spin faster. So that's actually true for a lot of young stars. You see the more massive stars, they spin much faster. And what plays a role is more on the magnetic field strength, not the radiation. That's because the plasma beta here is close to 10 to the -5. It's highly magnetized regime. So the thermal pressure or thermal radiation does not play much role compared with magnetic. So it's more depends on the stellar magnetic field, how strong it is, whether you have enough convective, like young star, you have in convective environment to produce very strong magnetic field. But for massive star, they don't have that strong magnetic field. So then the piece is much smaller. Okay. So they rotate much faster.
I had two questions, but maybe they're related. So what happens when material actually like reaches the star? Like, does it go through the star? Do you just spread it out on the surface?
Yeah, they will form a shock. The material will, because you have a free fall material at very high speed, 100 kilometers per second, and free fall to like a stellar surface much higher density. So they will immediately form a shock. And that shock is a strong shock. The shock will be 1 million degrees. So they will radiate that X-ray. Then you have post-shock region and the pre-shock region. So then the material will, post-shock region material will add to the star. They will actually get into the star. But the X-rays will be absorbed by the post-shock region and they will rethermalize because the X-ray mean free path is very short. So this whole region will get hotter around. So this post-shock region will be quite hot. Like it will be less hot, will be colder than the 1 million. It will be several thousand Kelvin, but still hotter than your surrounding photosphere. So that's why you could see them at UV. Yeah, so that will, what will happen? They will end up into the star. They will be part of the star.
Okay. And for the hotspots, you calculate the temperature just by the temperature of the initial shock?
No, the hotspot, the first order calculation is you use the total kinetic energy, rho v cube, the kinetic energy flux equals sigma T4. So you assume all the kinetic energy will be radiated away. Okay. So that's the first order calculation. That normally is pretty good. In our simulation, we haven't carried out radiation hydro, so we don't actually know the temperature. But observationally, that's how people calculate the shock temperature.
Okay, thanks.
Yeah, I had a quick question earlier when you were talking about the planet disk interactions and how you have, when you have the elliptical orbits that leads to the supersonic velocities. Is this because of the differences in how the Lindblad torques operate from the inner and outer wakes? Because when you have a kind of circular orbit, the Lindblad torques are kind of directly on the wakes. Does the direction of the Lindblad torques have a kind of role in this? And is the kind of development of the Lindblad torques different when you have this elliptical regime?
Yeah, so Lindblad, in the circular case, the Lindblad torque normally is damping the eccentricity. So if you have a small eccentricity for the companion, the Lindblad torque will damp your eccentricity to make the circular. So you do not actually expect a lot of planet will become eccentric orbit. On the other hand, if you open a gap, the story becomes trickier because you have truncate some of the Lindblad resonances, but not all of them. Then they can start to drive eccentricity. So that's still very active research area. It's very difficult to simulate in numerical simulation because first, study migration is difficult. You have two Lindblad torque, the gradual interaction with two spiral arms. You have two big forces subtract each other. It's already difficult. And now you are talking about the second order effect driving eccentricity. So in simulation, I think it's very hard to convince people that my simulation could drive eccentricity or not. But then most of the eccentricity calculation were from analytical calculations.
Just to add on to this, because like when you have the formation of annular gaps, right, the Lindblad torques becomes more dominant than the viscous torques. So wouldn't that have a role in producing the eccentricity?
So most of the damping of the eccentricity is from the co-orbital region. So when you open a gap, you are left with resonances which more drives eccentricity. So that's Goodreich and Sari proposed in 1995. But people are still trying to simulate those gap system with eccentric drive, but it's still not quite clear whether when you have a Jupiter can drive high eccentricity.
So I just want to ask about the thing you mentioned about migration being slow near the
inner part of
inner part of the disk. So in that case, you're basically predicting that migration will at most terminate at the inner edge of the disk.
That's all. Yeah, that's what.
Yeah, is that consistent with, say, the
Observation.
the observation of super Earth sub-Neptunes? I thought they seem to pile up at
You have a lot
slightly
of
closer in.
So for these hot Jupiters, I'm talking with Jiaying, these hot Jupiters, it seems people think most of them come from high migration later on. So they may not actually be in the disk at this small distance at early on. But on the other hand, there are observations like CI tau where they claim they detect a planet close to the star. So if that's a real young planet in the photogenics, that our scenario could apply. But why they migrate to here, it could be at an early stage. And your question is whether this is consistent, right? Like whether how the planet could populate this area.
Right, because for hot Jupiter, like we often say, there's some like uncertainty between this migration and high migration. But for low mass planets, somehow, I think the sort of common sense now, which may be wrong, is that they undergo this migration.
Yeah.
So
So
you're
we're actually
saying we should rethink that as well.
we're actually studying another process not in here, is a stochastic migration to turbulence. So we actually, I have a slide. To show that that's one thing we are thinking which may help. Stochastic migration. So because of turbulence, the planet will undergo stochastic migration. But the stochastic migration is not a traditional stochastic migration in a turbulent disk. You actually have these additional peaks modulation. And this modulation is due to this planet is interact with its filaments. So this filament gradually interact with the planet produces like sinusoidal perturbation. So we have a new theory on the migration. So this is something we try to see. If we have low mass planet here, and with this new Gaussian process for migration, whether we could put some of them inside the inner disk. So that's one way, which may work, which may not.